I, Dr. Emmanuel John Raja, welcome you to the session on building BGP peering session. We'll have a walkthrough of the negotiation process between BGP and its neighbors. Although BGP is used to provide a loop-free interdomain topology, BGP is also used internal to an autonomous system to provide internal routes with external destination reachability information. A neighbor connection, also referred to as peer connection between two routers, can be established within the same autonomous system, in which case BGP is called internal BGP, in other words IBGP. Similarly, a peer connection between routers in different autonomous systems is referred to as external BGP, in short EBGP. The difference between EBGP and IBGP is visible in how each peer would process the routing updates coming from the other peer and in the way different BGP attributes are carried on external connections versus internal connections. The neighbor negotiation process is the same for internal and external neighbors as far as building the TCP connection at the transport level. It is essential, please remember, it is essential to have IP connectivity between two neighbors, BGP neighbors, for the transport session to be established. IP connectivity must be achieved via a protocol which is different from BGP. Otherwise, the session will be in a race condition. Let me explain this issue. Neighbors can reach one another via some interior gateway protocol. The BGP session is established and BGP messages are exchanged. The IGP connection goes away for some reason. There could be some reason why the network loses the IGP connection. But the BGP TCP session is still up because neighbors can still reach each other via BGP. Eventually, the session will go down because the BGP session cannot depend on BGP itself for neighbor connectivity. This is very important point for us to work on BGP. Generally, for external BGP sessions, a route through a directly connected interface establishes IP reachability. Subsequently, we'll talk more on physical versus logical connections. As you have just seen, external BGP neighbors have a restriction in that they must be physically connected adjacent to one another. BGP drops any update message from its external BGP pair if the pair is not physically connected unless otherwise specified. However, some situations arise in which external neighbors cannot be on the same physical segment. Such neighbors are logically connected but not physically connected. A best example would be running BGP between external neighbors across non-BGP routers. BGP would require some extra or additional configuration to indicate that its external pair is not physically attached. A BGP session formed between external BGP pairs that are not physically connected is referred to as multi-hop EBGP. Let's have a look at the exhibit shown. RT2 cannot run BGP, but RT1 and RT3 can run BGP in this exhibit. Thus, external neighbors RT1 and RT3 are logically connected and pair with one another via multi-hop eBGP. However, a BGP must somehow learn the appropriate routing information to avoid potential forwarding loops or a problem called black holing of packets. On the other hand, neighbors within the same autonomous system have no restriction whatsoever on whether the pair is physically connected or separated by multi-hop IP hops. As long as there is IP connectivity between two neighbors, BGP requires no additional configuration. RT1 and RT4 are logically but not physically connected because both are in the same autonomous system. No additional configuration is required for them to run IBGP. Let's proceed to know the importance of IP addresses of the interfaces and their impact on the route stability. The neighbor's IP address could be the address of any of the router's interfaces such as Ethernet, token ring or serial interface. Keep in mind that the stability of the neighbor connection heavily depends on the stability of the IP address you choose. If the IP address belongs to an Ethernet card that has some hardware problems and is shutting down every few minutes, the neighbor connection and the stability of the routing system will surely suffer. Cisco provides the capability to configure so-called virtual interface. It is referred to as loopback interface that is supposed to be up all the times. Tying the BGP neighbor connection to a loopback interface will ensure that the BGP session is not reliant on any hardware interface that might be problematic. Adding loopback interfaces is not necessary in every situation. If external BGP neighbors are directly connected and the IP addresses of the directly connected segment are used for the neighbor negotiation, a loopback address is of no added value. If the physical link between the two pairs is problematic, the session will break with or without loopback. Let's move on to the BGP route summarization. By default, BGP requires that it must be synchronized with the IGP before BGP may advertise transit routes to external autonomous systems. If an iBGP speaker were to advertise a route to an external pair before all routers within your autonomous system had learned about the route through the IGP, the autonomous system could receive traffic to destination for which some of the routers might not yet have the information to reach. Whenever a router receives an update about a destination from an iBGP peer, the router tries to verify internal reachability for that destination before advertising it to other eBGP peers. This router check indicates whether non-BGP routers can deliver traffic to that destination. Assuming that the IGP recognizes that destination, the router announces it to other eBGP peers. Otherwise, the router treats the destination prefix as not being synchronized with the IGP and does not advertise it. Consider the figure shown. ISP1 and ISP2 use ISP3 as a transit autonomous system. ISP3 has multiple routers in its autonomous system and is running BGP only on the border routers. ISP3 is running an interior gateway protocol inside the autonomous system for internal connectivity. Assume that ISP1 is advertising a route 192.213.10/24 to ISP3 because RTA and RTCs in ISP3 are running iBGP. RTA propagates the route to RTC. Note that other routers beside RTA and RTC are not running BGP and have no knowledge so far of the existence of the route 192.213.10/24. If RTC advertises the route to ISP2, traffic toward the destination 192.213.10/24 will start flowing towards RTC. RTC will perform a lookup in its IP routing table and will direct the traffic towards RTB. RTB, having no visibility to the BGP routers, will drop the traffic because it has no knowledge of the destination. The traffic is dropped because BGP and IGP are not synchronized in this example. The BGP rule states that a BGP router should not advertise to external neighbors destinations learned from iBGP neighbors unless those destinations are known via an IGP. This is known as synchronization. Hope you got this. If a router knows about this destination via an IGP, it assumes that the route has already been propagated inside the autonomous system and internal reachability is ensured. The consequence of injecting BGP routes inside an IGP is costly. Redistributing routes from BGP into the IGP will result in major overhead on the internal routers, primarily from an IGP stability perspective, because IGPs are not designed to handle that many routes. Besides, carrying all external routes inside an autonomous system is totally not necessary. Routing can easily be accomplished by having internal non-BGP routers default to one of the BGP routers. Of course, this will result in suboptimal routing because there is no guarantee that the shortest path to reach route will be used. But this cost is minimal compared to maintaining thousands of routes inside the autonomous system. Of course, managing default routes in a situation such as this can be extremely complex and may very well result in routing loops. Most BGP implementations, however, offer a software knob that lets the network operator disable the synchronization. In practice, most situations allow synchronization to be safely turned off on border routers, assuming that all transit routers in the autonomous system are running fully meshed iBGP. In this situation, internal reachability is guaranteed because a route that is LANed via eBGP on any border router will automatically be passed on via BGP to all transit routers. By far, the most common configuration in internet connected networks is to disable BGP synchronization and rely on a full mesh of iBGP routers. The thought of injecting tens of thousands of routes into an IGP is quite frightening. As we progress in this session, we learn building peering session with few examples. An iBGP peering session is formed within Autonomous System 3 between RTA's loopback address and RTF's physical address. eBGP sessions are also formed between Autonomous System 3 and Autonomous System 1 by using the two directly connected IP addresses of RTA and RTC. Another eBGP session is formed between RTF in Autonomous System 3 and RTD in Autonomous System 2 using IP addresses that are not on the same segment, multi-hop. It is important to remember that the BGP TCP connection will not become established unless there is IGP connectivity between the two peers or the two peers are directly connected. Well, we will use OSPF as an IGP to establish the required underlying connectivity internally. Let's proceed to see the basic configurations. The configuration of the router RTA is shown on the screen for you. Let me quickly explain the requirement of the unfamiliar commands. One of the commands is IP subnet 0. This global configuration command is necessary in case you are configuring interfaces that fall in subnet 0 subnets, that is 192.168.10/30, when the mask is 30. With the introduction of classless routing, using a subnet 0 is very common and it is a recommended default configuration. The other one is interface type loopback 0. This command configures an interface type and number on the router. Any configuration that appears under the command will be specific to that particular interface. The loopback interface is a software only interface that emulates an interface that is always up. Please remember, it is not physically available. It's a software based interface which is expected to be up all the time. Router process with the process ID. This is a global command that defines a process such as OSPF, RIP or BGP and gives the process a process ID. Some processes such as RIP, that is Routing Information Protocol RIP process, do not require a process ID. For example, in RTS configuration, router OSPF 10 indicates an OSPF process with ID 10, whereas router BGP 3 indicates a BGP process in autonomous system 3. Next is no synchronization command. This command turns off the synchronization between BGP and IGP, which we have seen in the earlier slides. Remote AS, remote autonomous system. This command, when associated with the BGP neighbor statement, specifies the autonomous system number of the remote BGP peer. In RTS configuration, the first neighbor statement indicates that the internal BGP neighbor 172.16.1.2 belongs to the local autonomous system 3. The third neighbor statement indicates that the external BGP peer 172.16.21 belongs to autonomous system 1. Update source interface. This command, when associated with the BGP neighbor statement, specifies the interface to be used as a source IP address of the BGP session with the neighbor. In RTS configuration, for example, the second neighbor statement indicates that loopback 0 is to be used as a source IP address. This shows the RTF configuration. In RTF's configuration, you can see the eBGP multihop 2 command is used as part of the neighbor configuration. This indicates that the exterior BGP peer is not directly connected and can be reached at a maximum of 2 hops away. Remember that eBGP multihop is applicable with only eBGP, not iBGP. Also, the value at the end, 2 in this example, represents the TTL, time to leave value, to be configured in the IP packet header. The configurations of RTC and RTD are shown in this slide. From RTF's point of view, neighbor 172.16.2.254 is an internal neighbor that belongs to AS3. The neighbor connection is running BGP 4 with the table version of 2. The table version changes every time the BGP table is updated. RTF's other neighbor 192.68.12.1 is also in an established state. This external neighbor belongs to AS2, Autonomous System 2. Please note that the display indicates that this neighbor is 2 hops away as configured in the eBGP multihop. Well, that's all for this session. I am eagerly waiting to meet you during my another session on route filtering and attribute manipulation.